Hello, in this video we'll discuss the integral test. This is the first of many tests we'll look at to determine the convergence or divergence of series of positive terms. So we're going to start this video by reviewing the notion of infinite series. What does it mean for an infinite series to converge or diverge? And we'll talk about the reason we're focusing on series of positive terms. Let's let summation k equals 1 to infinity a sub k be an infinite series of non-negative, or if you like, positive terms. And we define the nth partial sum of the series to be the sum of the first n terms, k equals 1 to n a sub k, or a1 plus a2 plus, and so forth, on out to a sub n. As defined in section 10.2, or seen in our video on the definition of the sum of an infinite series, the series is defined to be the limit of the sequence of partial sums. So the summation k equals 1 to infinity a sub k is the limit as n goes to infinity of the sum k equals 1 to n of a sub k, and that sum from 1 to n is the partial sum s sub n, so we have the limit as n goes to infinity of s sub n. Now, we've said the terms a sub k are non-negative, that is, they're greater than or equal to 0. And so if we look at the various partial sums, S1, S2, etc., we see that those get larger, or at least they don't decrease, as we go further and further out in the sequence. So the non-negativity of the a sub k means the sequence of partial sums is a non-decreasing sequence. As we saw again in our previous video, and in fact in our opening discussion of sequences, a sequence that is monotone increasing or non-decreasing, if you like. There's two options. It either converges to a finite number s, or it diverges to positive infinity. This sequence cannot oscillate, so there's only these two options, either convergence or divergence to infinity. So again, applying this to the partial sums, of course, that means that this infinite series either converges to a finite sum s or diverges to plus infinity. So for an infinite series of non-negative terms, if we can convince ourselves that there is a number m such that the SNs are all less than or equal to m, so if that holds for all partial sums Sn, then we will know that the limit of the sequence cannot be infinity, because it cannot get above the number n. We'll be able to conclude then that this infinite series converges. And on the other hand, if there's no such m, that is, you give me an m, and I can always find some n to make Sn bigger than m, then we'll know the sequence Sn diverges to plus infinity, and the series diverges to plus infinity. So the integral test gives us one way of determining the existence or non-existence of such an upper bound m. And the integral test produces such an m usually as the value of a convergent improper integral. So here's what the integral test says. Let summation k equals 1 to infinity a sub k be an infinite series of positive and decreasing terms. So that is, the ak's are positive, as we see here, and as you move out in the sequence of terms of the series, that sequence is not increasing. So a1 big equal to a2, big equal to a3, etc. We'll see why this is important later on in the video. Now, we also assume that there is some function that generates the a sub k's. So we say there's a positive continuous function f of x that is decreasing also, and defined on the interval from 1 to infinity, and such that we get the a sub k's by replacing x by k in the formula for f of x. And this happens for k equals 1, 2, etc. So this was a long, complicated statement. What it really means is just there's some function f that is decreasing, and so that a sub k is f of k. So if I look at the summation k equals 1 to infinity of a sub k, that is the same as the summation as k equals 1 to infinity of f of k. And finally, the conclusion, if this all happens, then the series summation k equals 1 to infinity a sub k and the improper integral 1 to infinity fx dx either both converge or both diverge. So in other words, knowing what happens to the integral tells us what happens to the infinite series. So our goal will be to find a function f of x that relates to the infinite series as described above. And then if we can determine whether the improper integral, 1 to infinity f of x dx, is convergent or divergent, we'll be able to say the same thing about the infinite series. Furthermore, we're going to see that we'll get a little bit of information about the sum. If we have such a function f of x related to the infinite series, then the infinite series itself is going to be trapped between the improper integral and the number a plus that same improper integral. So this gives us a little information about the size of the sum of the series, if that series converges. And likewise, from this inequality, we can see that if this improper integral diverges, that is, if it's plus infinity, then the series being bigger would have to also be summed to plus infinity, that is, would have to diverge. So let's take a look at an example. Let's study the infinite series summation k equals 1 to infinity, square root of k over k plus 1, and determine whether it converges or diverges. So in this case, we're going to use the integral test with the function f of x given by root x over x plus 1. And we note the things we have to check off, that the function f of x is non-negative or positive. It's continuous on the interval from 1 to infinity. In particular, the denominator is never 0, and we're only concerned with x's that are positive. And finally, for k equals 1, 2, 3, etc., fk is equal to a sub k. We also have to check that the function f of x is decreasing on the interval from 1 to infinity. A couple ways to do that. The first way is probably not quite proper, but it'll generally suffice for us. You can just graph the function y equals f of x, and we can see from the graph that this function appears to be decreasing. In other words, the graph heads downward. Now, keep in mind that once we have shown that f of x is decreasing, then we also know that a1 bigger than a2 bigger than a3, etc. That is, the series terms are also not increasing. So even though we want to make sure those terms are decreasing to begin with, once we've shown that the f of x function is decreasing, that again shows us that a1, which is f of 1, bigger than a2, which is f of 2, etc. In Calculus 1, we learned other ways to show that a function is decreasing, and one way is to take a look at the derivative. So we can actually investigate f prime of x if the graph doesn't quite convince us the function is decreasing. So using the quotient rule, the derivative of root x over x plus 1 is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the square of the denominator. And those derivatives are pretty easy to take. They're given over here in this next step. And then a little algebraic simplification gets us to this point. And we notice that as long as x is at least as big as 1, this numerator is going to be less than or equal to 0. It'll be 0 when x equals 1 and negative for any larger values. The denominator is positive. So sure enough, this derivative is negative. And so the function f decreases. So with this f of x in place, we can now determine the behavior of the series by simply determining the behavior of the improper integral. So our next step then is to evaluate this improper integral 1 to infinity, root x over x plus 1 dx. And we go back to our definition of improper integral. We want to take a finite integral from 1 to some number b of that integrand, and then take the limit as b goes to plus infinity. We can evaluate this integral with an easy substitution. Let's set u equal the square root of x, and then we find that du is 1 over 2 root x dx. And remember, root x is equal to u, so that's also 1 over 2u dx. And that tells us when we solve for dx, we can replace dx by 2u du. We've done that in the next slide here. So the change of variables, we now have the following. 1 to infinity x plus root x over x plus 1 dx is the limit as b goes to infinity, integral from 1. Now the new upper limit with root x equal u is going to be root b. And then we have u squared plus 1, 2u du. And of course, as we saw earlier, this is the du, the dx here. And that corresponds to root x, because root x is u. And you see where the u squared plus 1 comes from. To evaluate that integral, we can notice that we can rewrite this as 2 minus 2 over u squared plus 1. What we've done in this stage is we've taken this integrand, which is 2u squared over u squared plus 1, and then we've added 2 and subtracted 2. And when you split this into two fractions, this one reduces to 2 and the other becomes minus 2 over u squared plus 1. So we just did that because then we can identify this new integral as just the sum of two very easy things to antidifferentiate. So as a result, we come up with the antiderivative of 2 turns out to be 2u, and we recognize 1 over u squared plus 1 as the derivative of the arctangent function. And so we come up with this integrand, put in the upper and lower limits of b and 1. Arctangent of 1 is pi over 4. And as b goes to infinity, the arctangent of b tends to pi over 2. And then most importantly, this factor in front, the 2 root b, becomes infinite, which gives us infinity here. So this shows that the improper integral diverges. And because the improper integral diverges, the infinite series, sum k equals 1 to infinity, root k over k plus 1 also diverges. Once again, the behavior of the improper integral coincides with the behavior of the series. So this is an example of how the integral test is used. Now we're going to pull this example apart a little bit more and get some insight into how the integral test works, how it relates to the series. And this insight is very important because you'll want to use this in some future exercises to estimate errors if you use a partial sum of a series to estimate an infinite series. So we've drawn this picture here. The blue curve is the graph of y equals f of x or root x plus 1. And the red are kind of left endpoint determined rectangles, and the kth rectangle has base that goes from k to k plus 1, as you see here, and height is determined by the height of the curve at that point. In this case, each rectangle has an area equal to a term of the series. So what we see here is, for example, this upper left point here has coordinates 1, f of 1, but remember f of 1 is a1. And so this rectangle is a 1 by a1 rectangle, a1 height, 1 width, and so has area of a1. The next point here has x coordinate 2 and y coordinate f of 2, but again f of 2 is a2. And so this gives us a rectangle with area a2 here, and similar things happen across the spectrum here. And we've stopped here at the nth rectangle that goes from n to n plus 1. So from this picture, we see that the nth partial sum of the series, that is this thing, or this, if we replace ak by f of k, is actually equal to the sum of the areas of those red rectangles. So if I add up this area, this one, etc., all these areas, I just get S sub n. And now from the picture, it's very clear that because all those rectangles lie above the curve, this sum is greater than the area under the curve, under the graph, for x's between 1 and n plus 1. I want to add here, this is why the idea of the series of the terms ak being decreasing is so important, and f being decreasing. If the function's decreasing, these left endpoint rectangles all lie above the graph. And because they all lie above the graph, we can make this statement about the sum of the rectangles being greater than the area under the curve. If the function were not decreasing, we wouldn't have this picture of all these rectangles uniformly above the graph. So the consequence is this. Now as we go to look at S sub n, the nth partial sum of the series, this is the sum of the a sub k's, k equals 1 to n, or the sum of root k over k plus 1 as k goes from 1 to n. And here's the area under the graph. We decide the sum of the areas of those rectangles is bigger than that area. And so we come up with this inequality. The partial sums are bounded below by this integral. And now if we let n go to infinity on both sides, we see that the sum of the series, which is the limit as n goes to infinity of the partial sums, is at least as big as the limit as n goes to infinity of the, say, partial integral, the integral from 1 to n plus 1. And of course, that's just the integral from 1 to infinity, the improper integral. So this kind of illustrates how this sum, the series, is bigger than the integral over here. And because that integral diverges, we know the infinite series must also diverge. And this is divergence to plus infinity. Okay, what do you want to remember from this video? Well, it's very important to check the hypotheses of the integral test if you're going to use it. In particular, you have to make sure your function f of x is positive and continuous and, perhaps hardest to check, decreasing on the interval from 1 to infinity. And it must also generate the terms fk equals a sub k. Often you'll find to get fk, you just have to pull the term out of this infinite series and replace the k's by x's, and that'll work. And remember, you may have to prove f of x is really decreasing. You might try this with a graph, or you could use the first derivative and see that that first derivative is non-positive. And secondly, our analysis after the example was very important, our picture with rectangles. That analysis showed us that the nth partial sum, S sub n, or summation k equals 1 to n a sub k, or summation k equals 1 to n f of k, is bigger than the partial integral, 1 to n plus 1 f of x dx. And we saw then that by taking the limit on both sides of this, that we could see that the sum of the series was at least as big as the improper integral. And this is why we know that if this integral is plus infinity, as was the case in our example, then the sum is also plus infinity. In the next video, we'll see how the integral test leads to a bound on the left-hand side here, and that's how we conclude convergence. But we'll see that in the next video. Okay, thanks for listening. We'll see you in the next video.